Simple harmonic motion is a special case of periodic motion in kinematics. We talk about periodic motion if a moving body repeats its path in equal intervals of time. In the case of simple harmonic motion, a body performs a repeated back and forth movement over the same path about an equilibrium position. The maximum displacements of the body on the opposite sides of its equilibrium position are equal. This repeating motion with an equilibrium position between two turning points is also called harmonic oscillation. The trajectory of a body covers a complete cycle of the oscillation. If it leaves its equilibrium position, reaches one of its maxima, returns to its equilibrium position, leaves it in the opposite direction, reaches its other maximum, and returns to its equilibrium position again. There are many examples for such a type of motion in our everyday environment. A well-known example is the pendulum clock, where the pendulum performs a periodic motion. The bob on the end of the pendulum swings back and forth along an arc. It follows the same path in each period, the vertical position in its equilibrium and the two turning points on the opposite sides of the equilibrium position. If we project the motion of the bob on a horizontal line, then its horizontal position performs a harmonic oscillation along the line. Another example for harmonic motion is the group of waves on the water surface. The propagating waves repeat themselves for several cycles and are associated with simple harmonic motion. However, in a strict sense we have to speak of damped harmonic motion since the waves die out quickly. Sound, for example produced by musical instruments, is also a form of the harmonic motion, where the vibrations of the air propagates in every direction, and their damping is not so drastic as in the case of the waves on the water surface. The classical example for such a type of motion is the motion of a spring. If we stretch or compress a spring with one end fixed, then it starts oscillating. Its oscillating end performs a one-dimensional motion around its equilibrium position, which provides a convenient method to study simple harmonic motion. A spring oscillator consists of a spring, fixed with one end, and a body attached to its other one. Here we can see an apparatus with a vertical spring attached to a weight sliding on a guide rail. The displacement of the weight along the axis of the spring can be measured with a ruler. Let us start with the main property of the equations of motion for simple harmonic motion. If the position vector of the body performing harmonic oscillation is given, then the velocity of the body can be obtained by differentiating it with respect to time, and its second-order derivative is equal to the acceleration of the body. Since the simple harmonic motion is periodic, the position vector r of the body at the time t is the same as the one at the time t plus the period of the harmonic oscillation, denoted with the capital letter T. If a function is periodic, then its first and second-order time derivatives are also periodic functions. That is, both the velocity and the acceleration of an oscillating body are periodic with the same period t. As a result, it is enough to study the motion during one cycle of the oscillation, since a complete cycle provides all the relevant information on the nature of the motion. Based on these statements, let us provide a graphic description of the harmonic motion. We can use the spring oscillator to produce the graph of the motion for an oscillating body. Here we can see a ball suspended on a spring, which is attached on the ceiling. By pulling the ball in the vertical direction, we stretch the string. If we release the ball, then it starts oscillating with the displacement x measured from its equilibrium position. We call this displacement the amplitude of the harmonic motion. The simple harmonic motion can be studied by using a double spring oscillator with a ball. Here we attached an inked brush to the ball and placed a sheet of paper under the oscillator, so that we can plot the motion of the body on the sheet. If we pull the ball in one direction along the axis of the springs and release it, then the body starts oscillating. At the same time, we can move the sheet with a uniform speed in the direction perpendicular to the harmonic motion of the ball. Then the motion of the ball consists of two kinds of motion relative to the sheet, which are superimposed to each other. The first one is the harmonic motion of the ball along the axis of the springs, and the second one is the uniform linear motion of the ball perpendicular to the direction of the harmonic motion. As a result, the brush attached to the oscillating body draws a wavy curve on the moving sheet. Since we move the sheet with a uniform speed, the length measured in the direction of its motion is proportional to the elapsed time. The wavy curve plotted on the paper starts from the origin O and passes through the points denoted with capital letters, covering the complete cycle of the motion. In fact, it is a graph of the sine function, and this graph can be interpreted as the amplitude versus time graph of the harmonic motion performed by the ball. The period of the oscillation is t, and its maximal amplitude is denoted with x0. The initial time is chosen such that the ball passes through its equilibrium position at the origin O and moves into the positive direction. Then it reaches the maximum value x0 in the point A, and returns to its equilibrium position in the point B. It passes through its equilibrium position, moves in the negative direction and reaches the maximum amplitude of -x0 in the point C. In end of the cycle it returns to its equilibrium position in the point D. The oscillating ball repeats this cycle with the period t again and again. Since the sine function has a period of 2 pi, the amplitude x is given by x0 times the sine of the ratio of 2 pi times the time t to the period of the oscillation. This equation describes the simple harmonic or sinusoidal motion. We will give the following interpretation of the harmonic motion. Let us consider a point mass p moving along a circle of the radius x0 with a constant speed. We chose the center O of the circle as a frame of reference, and we attach an axis of the polar coordinate system to it so that the axis coincides with the time axis of the sinusoidal curve shown in the right-hand side. Then the x-axis of the displacement of the harmonic motion will be perpendicular to the axis of the polar coordinate system. We describe the position of the point P on the circle with the phase angle phi, measured from the axis of the polar coordinate system. We can project the motion of the point mass onto the x-axis in the plane of the circle. Then we will see that the projected point performs a simple harmonic oscillation around the equilibrium point O along the x-axis with the maximal amplitude x0. Since the phase angle of the radius op is equal to 2 pi for a complete rotation along the circle, phi is proportional to the time of the rotation with the proportionality constant 2 pi divided by the period of the cycle. That is, phi is equal to the ratio of 2 pi times the time t to the period of the cycle. The projection x of the radius OP on the axis of the displacement is given by x0 times sine phi, which is equal to x0 times the sine of 2 pi times t over the time period, as we have already seen it. As in the case of the motion of the pendulum projected onto a vertical axis, the projection of motion of a ball attached to a rotating disk is harmonic motion. We can compare this motion with the oscillation of a ball suspended on a spring in the plane of the disk. By finding the proper speed for the rotation of the disk, the motion of the ball attached to it will coincide with the one of the ball oscillating on the string. In the graph of the amplitude versus the elapsed time we measure the time from the equilibrium position of the oscillating body. If the amplitude of the oscillation is arbitrary at the initial condition t equal to 0, then the general form of the amplitude x is given by x0 times sine 2 pi over the period times the time t plus an angle alpha. Here we used a phase constant alpha to shift the sine function along the time axis with angle alpha. At the time t equal to 0, the amplitude x of the harmonic motion is equal to x0 times sine alpha. For alpha equal to half of pi, the amplitude x becomes the maximal amplitude x0 at the time t equal to 0. Then we conclude that the amplitude x of the oscillation is given by x0 time cosine 2 pi over the period times the time t, which is completely equivalent with the original form of the amplitude as a function of time, apart from a phase shift of 90 degrees. Although the phase of the harmonic motion depends on the phase constant alpha, it does not change the nature of the motion. It only determines when the time measurement is started during the oscillation. Then alpha can be arbitrary for simple harmonic motion, and it will be chosen as 0 without loss of generality. In one cycle of the oscillation the phase angle phi runs from 0 to 360 degrees, and its different values represent different states of motion. Although for phi equal to 30 degrees and 150 degrees the amplitude x is the same, the body in the instantaneous moments represented by these phase angles moves in opposite directions. That is, the velocity of the body is different, which means it has different states of motion at the same location but with different phase angles or at different times. Now we introduce some quantities describing harmonic motion, which are equivalent to each other. We define the frequency nu of the oscillation as the reciprocal of its period t. Then it is measured in the reciprocal of second, and its unit is named after Hertz with the abbreviation Hz. The angular frequency omega of the harmonic motion is defined by 2 pi times the frequency nu, that is, 2 pi over the period t, and it is also measured in Hertz. The equation of motion of harmonic motion contains two parameters, its maximal amplitude x0 and its period t. Now we have two other quantities, the frequency nu and the angular frequency omega to describe the periodicity of the oscillation. Depending on which of the parameters are used in the equation, we can write it in three different but equivalent forms. In the original form of the equation of motion we use the period t of the oscillation, where the amplitude x is equal to the maximal amplitude x0 times sine 2 pi divided by the period of the oscillation, times the time t. If we apply the angular frequency omega instead of the period t, then we obtain the simplest mathematical form of the amplitude x, which is given by x0 times sine the angular frequency omega times the time t. We can also use the frequency nu in the equation of the amplitude x, which is then equal to x0 times sine 2 pi times the frequency nu times the time t. After having determined the first equation of motion for the amplitude of the harmonic motion, let us derive the other two equations for the velocity and the acceleration of an oscillating body. As we have already demonstrated, the amplitude x of the oscillation is given by the maximal amplitude x0 times sine 2 pi over the period of the oscillation, times the time t. If we use the angular frequency omega, then we can write the displacement as x0 times sine omega times t. We note that the phase of oscillation is given by 2 pi divided by the period times the time t, or omega times t. The amplitude of oscillation as a function of time is plotted in the right-hand side. Here the vertical dashed lines divide the complete cycle into 4 equal time intervals with the length of a quarter of the period t. The velocity of an oscillating body is the derivative of the amplitude x with respect to the time t. This gives 2 pi divided by the period t times x0, times cosine 2 pi divided by the period times the time t. We can substitute the angular frequency in this equation, and we obtain omega times x0, times cosine omega times t. If we compare the velocity versus time diagram with the graph of the amplitude versus time, we see that its graph is shifted with a 90 degrees in the negative direction along the time axis. The maximal value of the velocity is given by the angular frequency omega times the maximal amplitude x0. As in the case of the displacement x, the velocity function can also be represented by a vector revolving in a circle, but with the radius omega times x0 instead of x0. Here the magnitude of the velocity is given by the vertical projection of the vector, which is equal to omega times x0, times cosine phi. The phase angle phi of the vector is equal to 2 pi over the period times the time t, or omega times t. We can see in the figure, if the phase angle is equal to 0, 180, and 360 degrees, then the vertical projection of the rotating vector is maximal, that is omega times x0. For phi equal to 90 and 270 degrees, the vertical projection of the rotating vector vanishes. In this table, the velocity of the oscillating body is given at the time of 0, at 1/4 of the period, at the middle of the period, at 3/4 of the period, and at the end of the period. At t equal to 0, measured from the moment when the body passes through the equilibrium point, the velocity is maximal with the value of omega times x0. At 1/4 of the cycle, where the body reaches the turning point at the maximal amplitude at x0, its velocity reduces to 0. In the middle of the period, the body passes through the equilibrium position again, and the velocity is equal to minus omega times x0. That is, it has a maximum magnitude but points into the negative direction. At 3/4 of the period, the body arrives at the turning point with the maximal amplitude of x0 in the negative direction, and its velocity is 0. At the end of the cycle, the body goes back to its equilibrium position again with the maximal velocity omega times x0, pointing into the positive direction. Similarly, we can determine the acceleration of the oscillating body by differentiating the velocity with respect to the time t. We obtain minus the square of 2 pi over the period, times x0 times sine 2 pi over the period. This result can be written as minus omega squared times x0, times sine omega times t. The plot of the acceleration versus time is shifted with 180 degrees in the negative direction of the time axis with respect to the graph of the amplitude versus time. Its maximal value is given by omega 2 times x0. The acceleration can also be represented with a vector rotating around a circle. Here the radius of the circle is equal to omega squared times x0. The acceleration is given by the minus horizontal projection of the vector, which is equal to minus omega squared times x0 times sine phi. Since the phase angle phi is equal to 2 pi over the period times the time t, or omega times t, we regain the equations for the acceleration shown in the left-hand side. In the table, we can see the value of the acceleration at each quarter of the complete cycle. At the beginning of the period, the body passes through the equilibrium point, where its acceleration is 0. At 1/4 of the cycle, the body arrives at the turning point x0, where its acceleration has minus omega squared x0. The negative acceleration of a body is called deceleration. Thus the deceleration of the body is maximal in this point. In the middle of the period, the body passes through the equilibrium position again, and its acceleration vanishes. At 3/4 of the cycle, the body reaches the turning point at the maximal amplitude of x0 in the negative direction, where its acceleration has the maximal value of omega squared times x0. At the end of the period, the body goes back to its equilibrium position again, and its acceleration vanishes. If we compare the equations of motion or the graphs for the amplitude and the acceleration of harmonic motion, then we see that the acceleration can be expressed as minus 2 pi over the period times the amplitude x, or as minus the angular velocity omega squared times the amplitude x. That is, the acceleration of an oscillator is proportional to its amplitude, where the proportionality factor is minus omega squared. Then we can conclude the following. If a body is undergoing simple harmonic motion, then the acceleration of the body is directly proportional to its displacement measured from the equilibrium position, and it is always directed towards the equilibrium position. The converse of the statement is also true. If the acceleration of a body moving along a straight line is directly proportional to the distance measured from a fixed point, and it is always directed towards that point, that is, if the acceleration of the body is equal to minus gamma times the distance x of the body from the fixed point, where gamma is a positive constant, then the body is undergoing simple harmonic motion with the period of 2 pi divided by the square root of gamma. The period t of the oscillation can be determined by the comparison of the mathematical form and the relation between the amplitude and the acceleration for simple harmonic motion, stating the acceleration is equal to minus 2 pi over the period t squared times the amplitude x. Then we obtain that the square of 2 pi over the period t is equal to gamma. We can solve this equation for the period t, which gives the ratio of 2 pi to the square root of gamma. In this figure, we illustrate the relation between the amplitude and the acceleration of a spring oscillator with the maximal amplitude x0 and the angular frequency omega. Here we follow the motion of the oscillating body from its turning point at the displacement minus x0 to the turning point at x0. This motion is indicated with the green arrow pointing in the positive direction of the x-axis. In the position minus x0, the distance of the oscillating body from its equilibrium position is maximal, and its acceleration also has the maximum value of omega squared times x0. Here the body reverses its direction of motion, and starts to move in the direction of its equilibrium position. Therefore its acceleration vector points in the direction of motion, indicated with the upper red arrow. When the body passes through its equilibrium position and move away from it, the acceleration vector reverses its direction and points in the opposite to direction of motion, indicated in the lower red arrow. In the lower figure, we follow the motion of the body from the turning point at the position of x0 to the turning point at minus x0, which is indicated with the green arrow. In the position x0, the distance of the oscillating body from its equilibrium position is maximal. Its acceleration has the value of minus omega squared times x0, that is, its deceleration is also maximal. Here the body reverses its direction of motion and starts to move in the direction of its equilibrium position. Then its acceleration vector points in the direction of motion, indicated with the lower red arrow. When the body passes through its equilibrium position and move away from it, the acceleration vector reverses its direction and points in the opposite direction of the motion, indicated in the upper red arrow. Periodic motion can be described with complex numbers in physics, which provides a convenient representation for simple harmonic motion. Complex numbers are ordered pairs of real numbers, that is, a complex number z is given by the pair a and b, where a and b are real numbers. The first member a of the pair is called the real part of the complex number z, and the second member b is its imaginary part. We can represent the complex number z with a vector in the complex plane spanned by the axes of the pure real and the pure imaginary numbers. Here the projection of the vector on the real axis gives the real part a of the complex number z, and its projection on the imaginary axis gives its imaginary part b. The set C of complex numbers forms a field under the operations of addition and multiplication defined on complex numbers. The addition of two complex numbers, let us say AB and CD, gives another complex number with the real part of A plus C, and with the imaginary part of B plus D. The multiplication of two complex numbers is defined as follows. If we multiply the complex numbers A, B and C, D with each other, the real part of the result is equal to A times C minus B times D, and its imaginary part is given by A times D plus B times C. In the complex plane there are two units, the pair 1, 0 is the real unit, and the pair 0, 1 is the imaginary unit. The later one is denoted with I. If we multiply the real unit with itself by using the definition of the complex multiplication, where A and C are 1 and B and D are 0, then we obtain the real unit, that is the square of 1 is 1, as we expected. However, if we multiply the imaginary unit with itself, that is, if A and C are 0 and B and D are 1, we obtain -1, 0. As a result, the square of the imaginary unit I is equal to -1. This is an interesting result. It shows that, if the vector representing the imaginary unit, which points in the positive direction of the imaginary axis, is multiplied with itself, then the resulting vector with the same length points into the direction of the negative real axis. That is, we rotated the imaginary unit 90 degrees counterclockwise by multiplying it with itself. If we multiply the complex number AB with the imaginary unit I, we obtain -BA, which is the result of the rotation of 90 degrees counterclockwise. By applying the imaginary unit I, we can write any complex number in algebraic form, that is a complex number Z given by the ordered pair AB, can be written as A plus I times B. If we use trigonometric relations in the complex plane, then we can write the projections of any vector representing a complex number in terms of the length of the vector and the angle between the vector and the real axis. Here the length r of the complex number AB is equal to the square root of A squared plus B squared, and the angle phi is given by the tangent of B over A. Then the trigonometric form of Z equal to AB, is given by R times the sum of cosine phi and I times sine phi. Since Euler's formula states that cosine phi plus I times sine phi is equal to the exponential of I times phi, we can write the trigonometric form of a complex number in the exponential one, that is R times e to I times phi. This is the most convenient form of complex numbers. The exponential form of the imaginary unit I is simply e to I times pi over 2. If we multiply a complex number Z having the magnitude R and angle phi by the imaginary unit I, then we obtain R times e to phi plus pi over 2, as a result of the complex rotation by 90 degrees. We have represented simple harmonic motion with uniform circular motion, where we used vectors revolving in circles. The radii of the circles were equal to the maxima of the kinematic quantities, and the rotation of these vectors represented the change of the kinematic quantities in time. Here we can see a rotating vector in the circle of the radius x0, which is the maximum amplitude of the oscillation. The green vector represents the displacement vector, and its projection on the x-axis is equal to the amplitude x. Its instantaneous direction is determined by the phase angle phi, which is equal to the angular frequency omega times the time t. The next circle has a radius of omega times x0, which is the maximal speed of the oscillating body. The blue vector represents its velocity, which is perpendicular to the vector representing the displacement. The magnitude of the velocity is given by the projection of this vector onto the x-axis. The third circle has the radius of omega squared times x0, which is the maximal acceleration of the oscillating body. The red vector represents the acceleration, and it points in the direction opposite to the direction of the displacement vector. Its projection on the x-axis gives the magnitude of the acceleration. All the three vectors revolve around the circles with the angular velocity omega, and their projections determine the instantaneous kinematic quantities of simple harmonic motion. The plane of these circles can be interpreted as the complex plane with the real and imaginary axes. Then we consider the rotating vectors as the representation of complex numbers, and we use these complex numbers to describe the kinematic quantities. The real part of these complex numbers gives the magnitude of the corresponding kinematic quantity. Then the displacement x of the oscillation can be interpreted as a complex number, which is written in exponential form. Its magnitude is the maximum amplitude x0, and its exponential term is given by e to I times the phase angle phi. The phase angle of the rotating vector is equal to omega times t plus alpha. If the phase angle alpha is set to 0, then x is equal to x0 times e to I times omega times t. The velocity and the acceleration can also be written as such a form. As a result, the complex representation of the equations of motion for simple harmonic motion is the following. The displacement or amplitude is given by the maximum amplitude x0 times e2, I times the angular frequency omega times the time t. The derivative of this equation with respect to the time t gives the velocity of the oscillating body. Then the velocity is equal to I omega times x0, times e to I times omega times t. We saw that the multiplication of a complex number with the imaginary unit is equivalent with the rotation by 90 degrees. Then the velocity can be written as omega times x0 times e to I times phase angle shifted with pi over 2, that is omega times t plus pi over 2. This indicates that the velocity in the harmonic motion is shifted with 90 degrees relative to the one of the amplitude x, as seen in the figure. The derivative of the velocity with respect to the time t is equal to the acceleration of the oscillating body. As a result, the acceleration is equal to the square of I times omega squared times x0 times the exponential factor, where the square of the imaginary unit is -1. Then the acceleration is given by minus omega squared times x0 times e to I times omega times t. The multiplication with I squared is equivalent with the rotation of a vector by 180 degrees in the complex plane. Therefore the direction of the vector representing the acceleration is just the opposite to the one of the vector representing the displacement. These equations give the complex representation of the equations of motion for simple harmonic motion. We say that these are the equations of motions of the oscillation in the frequency domain. If we take the real parts of these equations, we obtain the equations of motion in the time domain for simple harmonic motion. Then the equation of motion of the amplitude of the oscillation is equal to x0 times cosine omega t. The velocity of oscillating body is given by omega times x0 times sine omega t, and the acceleration can be written as minus omega squared times x0 times cosine omega t. If we compare these equations with the equations of motions we presented earlier, then we see that they are shifted by a phase constant of 90 degrees with respect to the original ones. However, the phase constant has no importance in the kinetic description of simple harmonic motion. Therefore, these equations of motion represent the same type of motion. Let us finish the discussion about simple harmonic motion with a summary of its equations of motion. First, we give an overview of the equations of motion in the time domain. We saw that the simple harmonic motion is described with two parameters. The maximum amplitude x0 of the oscillation and another parameter, which can be the period t of a complete cycle, the frequency nu, or the angular frequency omega of the periodic motion. If we consider the choice of the second parameter, then we can arrange the different forms of the equations of motion in a table with the columns for the amplitude, the velocity, the acceleration of the moving body, and the parameters used in these equations. We start with the parameters x0 and omega, since the application of the angular frequency provides the simplest and the most popular form of the equations of motion for simple harmonic motion. The amplitude x of the simple harmonic motion is equal to the maximal amplitude x0 times the sine of the angular frequency omega times the time t. The velocity vx of the oscillating body is given by omega times x0 times cosine omega times t, and its acceleration ax can be written as minus omega squared times x0 times sine omega times t. We can use the frequency nu of the oscillation instead of the angular frequency omega. Then we obtain the equations of motion in the following form, where we replaced omega with 2 pi nu in each equation. In the original form of the equations of motion we use the period t of the cycle as the second parameter. Then we obtain these equations from the equations in the third line of the table by substituting the frequency nu with the reciprocal of the period t. An alternative form of these equations can be used if we apply a phase constant of 90 degrees, that is if we start measuring the time a quarter of a period later than we did for the equations in the table. As a result of this phase shift, we need to replace the function sign with cosine and vice versa in these equations. Therefore, the amplitude and the accelerations are functions of cosine omega t now, and the velocity depends on sine omega t. These equations can also be written in terms of the frequency nu or the period t. Second, we also show the table for the equations of motion in the frequency domain. If we use the parameters x0 and omega, the complex representation of the amplitude of simple harmonic motion can be written as x0 times e to I times omega t. The complex representation of the velocity of the oscillating body is given by I times omega times x0 times e to I times omega t, whereas the complex representation of the acceleration is equal to minus omega squared times x0 times e to I times omega t. If we use the frequency instead of the angular frequency, then we just need to replace omega with 2 pi times nu in these equations. Similarly, for the period t, we have the following equations for the kinematic quantities, where we have substituted 1 over t into nu. These are the equations of motion for simple harmonic motion with different sets of parameters, represented in the time and frequency domain.